Awesome. Good morning, everyone, and thanks the organizers for the invitation. This is a little bit of older work that was started by postdoc David Hooker, who's amazing, and I'm going to try to squeeze in a little bit of newer work by Jaden Lee, who was a KAIST undergraduate exchange student, and we're continuing to work together with a 12-hour time zone difference, which is fun. Yes, and the topic is how what you know already affects how you learn new things. Okay, and I'm going to ask you to do something very hard. Imagine a scenario where you're tasked to juggle multiple balls while riding a unicycle at the same time. Now, unless you grew up in a circus, you will not from the get-go try to learn to do this task. Yeah, that's the same. Instead, you're trying to breaking up into pieces and tackle those individually. So if you already know how to ride the bike, maybe you can use that knowledge to figure out how unicycles work. Then separately in parallel, you'll figure out how to do joggling, and you'll start small with a single ball, and then you work your way up to 6, 7, 8. Okay. I can't do any of these things, but this is sort of like that. That would be like a sensible plan to go about it. And sort of this graduate plan to mastery is very intuitive to us humans. So it's at the root of how our educational system works. It's also how we train animals to learn to do complex tasks in an experimental setup. But today I'll argue that this is also an important consideration when training artificial agents to model the behavior of animals in complex tasks. Okay, that's the plan. No juggling involved. So I'm using this example as a way of sort of communicating some key ideas. First of all, that you have multiple simple skills that are trained individually, and then sort of the target task is about putting those together in the right kind of way. Unlike the sort of motor task that Joe Patton was talking about in the main meeting, where you have a sequence of actions that you have to string together, or how hierarchical reinforcement learning works when you're planning with options. Here we're talking about a notion of compositionality of tasks, where you get to do multiple things in parallel, not necessarily in sequence. So that the unicycle and the joggling at the same time. And we're interested about the circuit level mechanisms. So, throughout the process, the learning that happens there. So we assume a setup where learning continues throughout. So the dynamical systems feature that the circuit learns during simple tasks gets reshaped by subsequent learning. And that's a bit different from if you know the work of Laura Driscoll or Robert Yang, where they either assume that the recurrent network doesn't learn anymore at target task time, or they're learning a bunch of tasks all jointly together. Okay. And what we were trying to understand is sort of the dynamical system signatures of the knowledge transfer between tasks. Okay, so we started this originally motivated by the attempt at building artificial agents that do context-dependent, value-based decision-making in Christine Constantinopoulos' task. And that was sort of described very effectively in one of the main meeting talks. I'm going to go through this bit very quickly. So the idea is that the animal initiates a trial by poking in the middle. You hear a tone that communicates 1 out of 5 possible reward offers, and that arrives, but at an unknown later time, which is drawn independently from an exponential distribution, leading to a flat hazard rate. And the animal needs to communicate how happy they are about this offer by the willingness to wait for it. So they have 2 options. It can either wait it out, or at any moment in time, it can sort of poke in the opposite port and restart the entire process. And in a small fraction of the trials, the experimentalist withholds the reward altogether, forcing the animal to engage in the opt-out option and giving thus this rich behavioral readout of what the animal thinks is it's worth it in this particular trial. The interesting part about the computational level is the context dependence. So you have different kind of blocks that have different statistics for reward, and we're interested in how the decision to opt out gets modulated by this underlying latent structure that is not explicitly cued to the animal. Okay, we're good with this. So we've done, we know from a large body of literature that the animals do well in this task. matching core features of a simplified MDP formalization of the task that assumes full knowledge of the task statistics, including treating the latent blocks as observed. So what are the key features here? Sort of like the reward sensitivity, so you wait longer for longer rewards, and the context dependence, that for the same volume of reward, like the 20, you wait a lot longer if it's the best of a set of crappy options than the other way around. We've heard already that this involves dynamic inference. So from trial to trial, I need to maintain and update beliefs about what kind of block, what kind of world I'm in order for that to affect my policy about how long am I going to I'm willing to wait for this particular reward offer. Like this task has very long temporal dependence. So like there are many seconds like where you need to keep track of environmental statistics. And this is hard for the animal to train. It takes 3 to 6 months to train a rat in a rat factory to do this. It's also very hard for artificial agents because it takes many thousands of steps to, like, you need to understand dependencies of very long temporal horizons, okay? So that's what makes it hard. That's why we need to do complicated things. So what we ended up doing is finding that without a very dedicated curriculum, you can't learn this task. And our solution was to take our RNNs to kindergarten. What this means is that you're taking the task structure that's coming from the MDP, and you like identify individual elements of computation that are important for solving the task as a whole. So you need to keep in memory the reward. You can train that with a little supervised learning objective. You need to keep track of time, separate supervised learning objective. And then you need to sort of like know something about the reward statistics, and like that means integrating inputs over very long time constants and things like that. So you can make little supervised tasks and sort of like train these skills into the RNNs directly. And after that, we're throwing the RNN into the experimental setup where they're doing exactly the same thing that the animal do. So the first part of the kindergarten experience, we're thinking about with like training the knowledge that the animal brings with it to the experiment, and the rest is literally one-to-one map what happens with the rat once it arrives at the rat factory. Okay. So doing this is enough to the architecture is pretty complicated. We have multiple modules. And it's sort of like it's a meta-RL kind of structure with extra heads, like readout heads for the kindergarten tasks, and the losses combines typical RL objectives with regularizers for the losses. But once you put all of this effort in, you actually get like agents that behave like the rat. And it's not that they have these core features that I mentioned already. They also have the nuances. So for the fact that the differences between blue and purple are much bigger than between purple and red at 20, stuff like that. And they also can recapitulate the dynamics of the beliefs under the hood, which in the animal we get by fitting a behavioral model. Okay, cool. So this was worth all of the trouble. Like computationally, you can see that doing it this way gives you substantial improvements in performance relative to agents where you train directly on the task, or like including only the behavioral shaping part of the procedure. And you need the full curriculum. So if you do lesions where you only take bits of the task, in particular, you do only the hard bit that explicitly trains for like integrating rewards over long time periods. That's not enough to get to good performance. Strangely enough, like having agents with extremely good working memory like is actually very beneficial, which is something that people were know before. But the curriculum is important for actually getting the details of the behavior right. So although you have similar offer and opt-out rates to the animals for both the green and the black, so working memory only and kindergarten, you see very different context sensitivity in the like waiting in the rats that don't see the full curriculum. So to recapitulate the full set of behavioral features, you need the full curriculum, and you need to model the full experience of the animal. Okay. So this is all stuff like you've seen this already in some form or the other. I think we've given previous talks about this. The the difference in computational strategy is kind of interesting. That means that maybe we can account across animal variability this way. But the point of today is the circuit level mechanism. So at the dynamical systems level, what happens to make this work? Okay. So these are very complicated networks. So opening the black box of the RNN, of the trained RNN, to understand what's going on under the hood is a pain, but we can do it. And you see structure like this. So this is an approximate two-dimensional flow field of the higher dimensional dynamics of the inference module. And what you can see very robustly across agents is 3 slow features shown in the black dots that correspond to fixed points or like approximate fixed points that are aligned to the axis of representing belief in what kind of block I'm in. So the color corresponds to if I'm in that particular region of the space, what does the network think, what kind of block the network thinks it's in, according to the block readout. Okay. You have like different trajectories corresponding to different beliefs. If you're sort of like believing that you're in a mixed block, so where all of the rewards are possible, and you see evidence of different kinds, so the different colors are now different reward offers in that particular trial, you're going to update your beliefs in a sensible manner. So if you get an 80 milliliter reward, that's really good. You're going to increase. You're going to go to the right, and you're more inclined to think that the world has improved than in your high block. And the other way around. If you get a very bad reward, you're starting to think that the work maybe is getting worse. Okay, so these are good because that means like at the level of the dynamics, we get mechanistic sense of what's going on computationally. If you're looking in the policy network at the decision-making part of the within trial decision-making part of the process, you see this a single fixed point that's in a blue region of the state space corresponding to increased probability of opting out. And these transient excursions towards that fixed point are reward dependent. So I'm making a bigger excursion if I get a really big reward. I'm waiting longer before opting out if I'm getting a big reward. Okay, so how about the learning process? What is it about the experience of all this sequence of tasks that allowed me to learn all this functionality? So if you're looking at the experience of a fully trained agent compared to simpler agents that get only partial aspects of the experience, you find that the circuits are learning a lot more like slow dynamical system structure. So they have like more things that they can do in terms of like maintaining information over time. And then that gets trimmed down and refined in the task period. If you're looking at exactly what happens with this dynamical systems motifs, you also see interesting things. So here's a 3D of the PC space of activity in the inference module. And this is like the average trajectory that I was showing before that sort of like signals what kind of block the agent thinks it's in. This is at the very end of training. You can plot in exactly the same PC space activity earlier in training, showing that basically I have a robust representation of this computation across learning periods. So I'm recycling this function over time. In the policy network, you see some structure, but that gets refined over time. So like they're like systematic reshaping of this part of the computation over learning. So we like this a lot because it sort of like points to a picture where the new experience is reusing and reshaping dynamical systems features that I brought with me from the earlier stages of learning. But these networks are super complicated and they're really hard to like analyze at the dynamical system level. So we decided to go simple and like look at like simpler task, vanilla RNN, same kind of phenomenology. So this is where Jaden got involved. Now we have vanilla RNNs trained on an evidence integration task with fixed trial length. And like this was kind of serendipitously, we found this version of the task that has a really crystalline, very pretty solution. Like Jaden calls it the bird cage. So what you can see is, again, like the 3D space of PC activity, and they're exactly the same dots corresponding to neural activity, colored either by time within trial in the first plot, or by evidence, like strength of evidence in the other. What you're seeing, like I'm keeping like both of these pieces of information in mind, and we can analyze the dynamical system structure of this thing much more precisely. So here I can show that the autonomous dynamics started in the middle of the equator of the bird cage, without any input, just go round and round and round and round. So I have a limit cycle along that dimension of the dynamics. Whereas along the vertical axis, I see almost no movement vertically in the absence of input. So all of the flow along the bar happens driven by the external input. So what we have is a weird collection of line attractors with one dimension of limit cycleness keeping track of, like as a clock keeping track of time. Okay, so this is funky because, again, like it's like the 3D flip-flop task. Like once you have a task with a funky structure, then you know what you're looking for, so you can go back into the learning process and see where it develops and how it develops in an interesting way. I don't have a lot of time to go through all of the details, but I'm going to show you like a couple of very quick results that should just see that this is actually a productive way forward. So again, like the thing that we're interested in is the curriculum and the roles of how that shapes the learning in the later process. So we decided to compare two curricula. So one curriculum is where you take the same task, but with like gradually increasing the length of the sequence, and that sort of like corresponds to this thing of like learning to juggle and adding one more ball at a time. This is also like the kind of meta learning that people typically use in machine learning to train their algorithms. And contrast that to the more kindergarten curriculum learning kind of thing, where I'm first training a keep track of time enterprise orthogonal to the computation that I actually want to do, and then bringing the integration on top of that existing structure. Okay, so thankfully, we find that, okay, in both cases, like having a curriculum is better than not. So knowing stuff about how the task works helps you at the end of the day, but it helps you much more in the kindergarten curriculum type of like enterprise. So when you're taking advantage of the compositional structure of the task. And the reason for that is sort of like goes back into the like opening the mechanics of the box. So whenever this like meta learning version helps is when you have like multiples of like increases that are multiples of each other. So if I know how to compute 6 by having a 6-bar bird cage, then I can reuse that structure like brute force by just cycling 2 times before I report my answer. But in the curriculum learning version, what you're learning is a collection of these punctate things with a limit cycle around it, and then building the line attractor like vertical dimension on top of that during the target task training time. So we're kind of excited about this because I think it's for the first time that you see compositional reuse of dynamics of this kind, where it's about like expanding or reshaping the individual dimensions of existing slow features. Okay, I have videos for everything because we like pretty videos. Okay, so with that, I'll wrap up. So what I've shown to you today is this idea of kindergarten curriculum learning as a way of mimicking, like better mimicking animal behavior when trained on complex tasks. And the idea is that in these like complex solutions, there are strong inductive biases that the animals bring with them to the experiments that come from their previous experience. And if you're not modeling that to some degree, or at least measuring it and try to sort of like take that into account, it's going to be difficult to make artificial RL agents that actually mimic the animals in a meaningful way. Then the metadynamics analysis, where we're looking at what happens with the dynamical systems of the RNN over the training process, reveals this like rich and interesting phenomenology related to reuse and reshaping of dynamical system structure. And the simple task we're really excited about because we think it might give us a more mathematically tractable way of understanding how these processes work. And it's sort of like, it has interesting links with to lazy and rich learning that I don't have time to talk about today. Okay, with that, I thank you for your attention. The work is done the first part of the work is done by David Hawker, and the birdcage phenomenon was described by Jaden Lee. And I'm happy to take questions. Mm-hmm. Mercurio? I can hear you, but maybe the Zoom people can't, but I can repeat the question.
Okay, do you mind just repeating the question?
Yeah.
Thanks, Cristina. I was wondering if you come up with those compositional sub-skills, given your understanding or the experimental understanding of the past, and then you see that the behavior matches with the animal. Do you see that as evidence that the animal also thinks this way and has those sub-skills? Or could it be that it has a completely different set of sub-skills but just converges to the same behavior?
That's a good question, and sort of like so the question is like, do the sub skills that we're identifying reflect the animal, an alignment between the animal's and experimentalist understanding of the structure of the task, or whether they're just epiphenomenal. I can't tell you what the rat thinks, so I don't have 100% clear answer to that. What I can tell you is that there is a like experimental agnostic way of identifying the curriculum in this particular case via the MDP. So because we have this like approximate mathematical description of what the task is, that sort of like skips some of the hard bits, but sort of like still tells you the coarse nature of the solution. That kind of tells you what are the individual bits of variables that you need to compute in order to do optimal behavior in this task. And like those one-to-one correspond to individual skills trained in the curriculum. Like if you had that in the context of a different task, you could do that without relying on sort of like experimentalists' understanding of what the task is about. In this particular case, they happen to align. So I can't tell you it's because this is like the fundamental math structure of the problem versus because these are the stories that we tell ourselves make sense. Yeah, I think we like. I'm hoping that people would do more of this. So like more of an experimentation in numerical versions of other kinds of tasks to see how general are the phenomena and how like if you find counterexamples where the intuitions don't align with the curriculum, that's best, or the computational like variables, as it were.
This is very inspiring. I was wondering maybe you can give us provide some thought on how applicable this compositional of dynamics to multi-churches talk on the compositional skills, where it also requires a very rapid switch.
Yeah. So the way I understand it, it's sort of like it's more like Laura Driscoll style. So you have an embedding or different kind of dynamic motifs already in a network. And then you're using inputs to decide which of them to actually engage computationally at each moment in time. So you have this control of a sequence of operations via the input. Like clearly that needs to happen too, because because these are also sort of it's still a dynamical system under the hood, and I'm still sort of like using the inputs to drive the nonlinear dynamical systems into regions of the space that matter at this particular moment in the task. But sort of like it kind of lacks this sequential structure, and it's a weird way of thinking about computation. Like this parallelization of computation is not something that's described often, and like I think we have like weaker mathematical tools to understand that part of the mechanics of the process, but they are different in that way. Yes.
So it seems like this is also a big question endeavor in large language models to get these things to, you ask it to do something and it breaks it down, that piece, and then it figures out what tools it needs to use. So I guess I wonder what the advantages or relative disadvantages of these RNN models are to, I guess, what they're doing, how we quantify, the approaches that they're taking.
Yes. So the LLM universe. Oh yes. If there are parallels or potentially interesting transfer between these RNN models of animal behavior and the use of the compositional use of LLMs, where sort of like they have policies deciding what kind of tools to use and how to use them in a semi-compositional fashion. I don't have a good answer for that. I just feel that they're very at the technical level, they're quite different objects. So in terms of understanding the mechanics, I don't know that the parallels are particularly tight. We do have this idea that's kind of crazy, and it's not what I presented today, that if I had a bunch of dynamical system skills. So I have different brain regions that through the course of evolution and past experience have been trained to do particular kind of compositional, particular kinds of elements of computation. So I have a region that does very good evidence integration, things like that. Then a controller in the brain that has can control what kind of inputs it flows into these different elements of circuitry, can get flexible way of building more complex computation out of existing elements. And there's a very cute anecdote where we see that happen in a task of virtual reality foraging in Dora Angelaki's lab, where you have this if you've heard about the Firefly task. So you have a little target flashing in a distance, and the monkey moves a joystick to move through the environment to get to this disappeared location, and then if it gets close enough, it gets a reward. And you only get optic flow to keep track of how fast you're moving through the environment. There are no landmarks. So the eyes are kind of free. You don't need to look at any particular location. And because of that, what the monkey chooses to do is externalize the working memory component. So I have this oculomotor system that's really good at tracking the locations of objects over time. Because I don't need to use that for its original purpose, the monkey chooses to use that just to keep track of where it wants to go, although there's nothing on the screen at that moment in time. So that's where this is coming from. There were more questions, sorry about that.